problem 24 is a nice little problem because it uses both um, net force x and net force y, and it's going to demonstrate this whole r perpendicular that I was talking about. And you'll use that in a few problems. So this is there's a wall, frictionless wall, and that'll become evident, the meaning of that, in a second. There's a floor with friction, and there's a guy leaning. I'm just going to draw like a bar. There's a guy leaning against the wall, right? And there's friction, static friction. He's not sliding, but he's just on the verge of sliding, which, if you remember from chapter 6, friction, the mu s that you get in that friction force is the coefficient of static friction just when you're on the verge of sliding. So nothing tricky there, even though it sounds tricky. The center of mass of the guy is like right here, I guess. And since there's no friction, there's no like up and down force on the guy of friction. So the only force acting at this point is the wall pushing back this way. So this is F wall, called FW. And we have, I'm going to draw mg, the weight of the guy acting at his center mass. You have the floor pushing up. We know that force. We know what that's called. That's a normal force. And to keep him from sliding back that way, we have friction pulling in. This is force of friction here. And we know some distances. Maybe I'll redraw this for the distances, because it's getting a little cluttered. So this triangle here is this triangle. So I guess I could extend this for the floor. So A is the distance between the wall and his feet. D is a distance D from his center mass to his feet along the floor, along his body. And L is essentially the length of his body. L. And that's it, I think. Yep. Excuse me. Alright, so we need, we got forces acting in two directions, right? Up, down, left, and right. So first off, let's just define direction of motion. Up, positive, down, negative, right, positive, left, negative. So we're going to need an F net x and an F net y and one torque equation. And we're going to have to pick a pivot point, so we'll discuss that in a second. So F net x. By the way, this is a good time to bring this up. Even though it's not the case for the sample problems I'm doing for you, sometimes you may not even need all of the equations. You may write out a F net x, F net y, and a torque net equation and realize I don't need the F net x, maybe. Or I don't even need the torque equation at all, or I just need the torque and not even any of the F nets. So, but you should still write them all out just in case, just to help you organize your thoughts. So F net x equals 0, always, because it's in equilibrium. And that's going to equal, so in the x direction we got two forces, force wall and force friction. Based on my direction of motion, F wall is positive and friction is negative. So I'm going to just play with this right now. So I'm going to add F to the other side, so we get force of the wall equals force of friction. And bringing back our good old knowledge, we know that force of friction is mu Fn. Ugh, gosh. Fn. And we'll leave this alone for now. Alright, so then we got Fnet y is 0, and there are two forces in the y direction. That's Fn is up, so that's positive, minus mg. So let's play with this a little bit. You know, Fn equals mg. Oh, so we could take that and go over here and say Fw equals mu mg. So we may not need any of those, but you know, let's just get it ready. That's pretty much all we can do for net forces right now. So let's do net torque. 0 equals. Now we gotta pick a pivot point. What are we looking for? We're looking for mu, right? Mu. So mu only appears over here, so we need Fw. So we probably don't want to pick Fw as our pivot, because system of equations, if we get rid of Fw in torque net, there's no way to get rid of it here. We don't know Fw. So based on that logic, I'm going to not make the pivot point at Fw. You can't even tell it's W, can you? So that's my logic for that. So that leaves either here or here. Well, we also have Fnet and force friction in these equations, but we also have mg. So you might be thinking, well, if we get rid of mg, if we pivot at mg, then for the same logic as Fw, that will get rid of that, so maybe we shouldn't do that, right? But let me see here. You know, this actually, I don't really know a good reason why. That's more of a intuition thing for me. My gut originally told me to pick it at mg and not here, but I just realized that the same logic as to why I didn't pivot at Fw is the logic is why I shouldn't pivot at mg. So I don't know how to unexplain that. The other thing is that this equation, you know what? At this point, I don't actually have an explanation for why. That is a valid explanation for why you shouldn't pivot at Fw, but I actually can't think of a good reason now for, except I just tried it and it worked. So sometimes it baffles explanation. You know, it's beyond explanation. So you may try to pick this as your pivot and realize, oh, that didn't work. Or actually, it may work. So two pivots may work. It's not always just one pivot point that's going to give you the solution. So anyway, I'm going to continue on with what I did and use mg as my pivot. So with that in mind, let me pause for a second and see if it works with these as a pivot. You know, it actually works, and it's actually easier to make the pivot point here. And the reason why it makes it easier is because it gets rid of two expressions in your torque. Like, if we make this our pivot, then we're going to have three forces in our torque net equation. This one, Fw, Fn, and Ff. But if we make this our pivot, then we only have two to worry about, this one and this one. So I'm going to do it that way, actually, and it makes the trig easier too. So that proves what I said earlier, that more than one pivot point can lead to a solution. So sometimes you'd want to, if you're able to, you want to pick the one that gives you the least amount of work, obviously. And so yeah, I'm going to make this the pivot point. And so that makes our torque equation Fw, which is going to make it go clockwise, and I'll do counterclockwise is negative. And we want the R perpendicular to FW. So if our pivot is here, then the perpendicular distance to the pivot point, so perpendicular to FW, is either up or down, right? And so our pivot is below, so we're going to go down, and so it's going to be essentially the length of this side of the triangle. So if this hypotenuse here is L, then our perpendicular here we'll call Y. It's like the height of this. So let's actually rename this as Y. And then minus mg, because this is our other pivot point, and it's going to make it rotate counterclockwise. Minus mg. And if I make this little triangle here, we'll call this, actually no, it's, yeah, we'll still make this triangle, but the mg is down, so perpendicular is left or right, and the pivot point is to the right of mg, so that distance, our perpendicular, is this distance, which is also this bottom leg of this little triangle here. So we'll call this x, just for the fun of it, so minus mgx. Alright, so we can figure those y and x lengths out pretty easily. One way to do it is, well, we can find this angle and use SOHCAHTOA. So what is that angle? We have L and we have A, so that angle is pretty easy to find. You just use cosine. So cosine of that angle is adjacent, which is A, over hypotenuse L. A, they gave us in the book, is 0.914, and L they gave us is 2.1. Right. So solve for theta, and you get theta is 64.1996 degrees. Alright. We could use Pythagorean to find y. We didn't need this angle, but I think we need that angle for this little triangle because we don't know either of the legs. Right. So anyway, using sine of this angle, so sine of theta equals y over L, we can get y, because we know theta now is 64, we know L is 2.1, so that means y equals I actually didn't, I'm going to pause because I didn't do this before because I made this my pivot point, so I'm going to just do my calculator without wasting your time. I'll be right back. I'm back. Alright, so y equals 1.89066. That will stick in here. So 0 equals 1.89066 FW minus, now let's find x. X I believe I did find, but where did I find it? That is, I think I did y2. Yeah, so this little triangle, we know that we want x, that's cosine, so I'll do that right here. Cosine of theta, which again is 64.1996, equals x over d, right? And d is 0.94, and so x is going to equal 0.409124. D was given in the book as 0.94, so we knew that. So solve for x, and that goes up here, so it's going to be 0.409124 mg. Now up here, we know that FW is mu mg, So we can replace that. So this becomes 0 equals 1.8906. So it looks like we didn't even need, no, we needed it for this, never mind. 8906 mu mg minus 0.409124 mg. 0 over here, and both terms have mg, so look what happens. The mg's cancel. That's cool. So now we can solve for mu, and we get the answer. Let me just verify that this is the. It is the same as one I got before, and so mu is 0.216392, and mu is unitless. Voila! So that's how you will do perpendicular distances. I hope I explained those well for you. Alright, next video, or next problem 30, I think.